the backdoor
URL
itself and
is
how it was working.
at the top, and then you have these slash for each
But
of the
before,
sub-options.
I want to
Or
talk
just
a
go
little bit about Andres and how he found the backdoor. Because on the internet, there was a kind of a legend where everyone was saying that the backdoor was discovered because of a 500 millisecond and from Andres that triggered the investigation. The reality is a bit different. Actually, what triggered the investigation from Andres was that he found that the SSH login in some of the testing he was doing was actually failing. So he decided to investigate a little bit more to try to understand why the SSH logins were actually failing. And he discovered that there was a substantial CPU usage during the SSH, and he found out the 500 millisecond delay, which he identified later in the new package XZ.
It's relatively new.
And he said itself, it was a bunch of coincidences. So if we have a look to how he discovered the backdoor, first, he saw that there was some issue with the SSH login. Then he decided to investigate, and then he found a little bit of amount of CPU using by the SSHD process. So he decided to investigate a little more, and he found out that this amount of CPU usage was used by the liblzma. But then that's now which is becoming a little bit crazy, because he actually used some specific setup which led him to find the backdoor. First, he decided to choose Debian unstable, which at the time of the release of the backdoor, only this kind of Linux version was affected by the backdoor. Then he chose to use a specific flag. And without this flag, he wouldn't have found the backdoor, because he was actually tracing the process using Valgrind, and Valgrind complained about the processes because of the flag he was setting up before. So that's super crazy, because thanks to that, he was able to investigate and to find that the high CPU usage was in the SSHD processes below get CPU ID. Keep that information in mind, because it will be interesting and important for the next part of the presentation.
More work, but I think that is the most.
But you may be wondering, what the fuck is the XZ utils package? So the XZ utils package is a free software, an open source software, which is dedicated for lossless data compression through LVCC algorithm and XZ. It is maintained by Lassicolin, which is the main maintainer of the backdoor of the package since more than a decade. The backdoor has been found in liblzma in the version of XZ 5.6.0 and 5.6.1, and it was introduced by a mysterious user called Jia Tan in February 2024. The package and the backdoor affected mostly development version, so it was not widely deployed when Andres found the backdoor itself. And Red Hat assigned the vulnerability CVE 2024-3094. There is something interesting here, because you may be wondering as well why the XZ utils package has in any relation with SSH. Well, I'm glad you asked. Actually, the XZ util backdoor package is widely used in many Linux distributions, and it's a trusted open source component for compression and any kind of optimization. The XZ util has been used in the open source industry for years, and which is interesting is that OpenSSH is using the XZ compression to reduce the size of transfer data when you are doing a connection. So, quite interesting target for an attacker. Okay, I want now to talk about the timeline. And it's a bit heavy, so what I did, I actually split the timeline into 5 different phases. The first phase, which I called initial involvement of Jia Tan, from October 29, 2021 to June 29, 2022. So during this phase, the user Jia Tan started to gain trust into the XZ project and started to do some commit and to work a little bit more. Which is interesting is during that phase as well, there were additional persona that was part of a kind of a pressure campaign against Laci Collin, the main maintainer of the XC package, to move the maintainership to another user. So some additional persona, such as Jigar Kumar and Dennis Hens, have been part of this pressure campaign to put the pressure on Laci Collin. And in June 29 of 2022, Laci Collin started to mention Jia Tan as a co-maintainer already. Then in phase 2, which I call transition of mentorship from September 27 of 2022 to March 18, 2023, during this time, Jia Tan continued to contribute to the project, to gain trust with the main maintainer and to the project itself. On October 2022, Jia Tan was added to the Tukeni organization on GitHub, which is the organization that released the XZ package. And then additional event as well during this time. Then during phase 3, which I call preparation for the attack from March 2023 to January 19, 2024. During this time, a bunch of information happened as well. First, Jia Tan updates the Google OSS first to send bugs to his own email. Then another persona, Ernst Jensen, sends patches for GNU indirect function features, which is quite important as well. And Jia Tan also disables iPhone support during the OSS first build, which is quite important because it's a kind of evading some security protections. And then during phase 4, which I call backdoor insertion and distribution from February 23 to March 28 of 2024, this is where Jia Tan started to release the backdoor. So in February 24, Jia Tan merged hidden backdoor binary code in kind of test files, which are actually fake test files. And then he released the version 5.6.0 with an additional file that was not present in the GitHub repository itself. And in March 9, Jia Tan committed an update of the backdoor because there was a bug, and then he released the version 5.6.1, which was backdoored as well. And then on the last phase, phase number 5, which I call discovery and response, from March 28 to March 30, this is where Andres found the backdoor, started to alert and to send the email with his own investigation, and this is where internet was on fire as well. But there is something which is interesting. I talk about the pressure campaign. So let me give you a little bit more detail about that, because this is quite interesting from the social engineering aspect. So first, I mentioned that some additional personas were part of this pressure campaign to move the maintainership of the backdoor to someone else. So in April 2022, Jigar Kumar sent a message. Patches spend years. In May 2022, Dennis Hens, the other persona, sent another message as well and said, I asked a question here a week ago and I have not heard back. It has not updated in over a year. Is there a plan for this thing in the future? Laci Collin, which at the time was getting all these messages from these personas, answered, Jia Tan has helped me off list with XZ utils, and he might have a bigger role in the future. It's clear that my resources are too limited. In May 2022, Jigar Kumar answered, over a month and no closer to being merged, not a surprise. Jigar Kumar sent another message, progress will not happen until there is a new maintainer. The current maintainer lost interest or doesn't care to maintain anymore. Quite aggressive. Then, on June 2022, Laci Collin answered, my ability to care has been fairly limited, mostly due to long-term mental health, but also due to some other things. Jia Tan may have a bigger role in the future. And he mentioned also, and I think this is quite important in this case, he mentioned it's also good to keep in mind that this is an unpaid hobby project. In June 2022, Jigar Kumar sent another message. Right now, you shock your repo. Why wait until 540 to change maintainer? Why delay what your repo needs? Dennis Hand sends the first time he asked Jia. Jia, I see you have recent commits. Why can't you commit this yourself? And then Lassie Colin reply on June 2022, on the day 29, Jia Tan may have a bigger role. He is practically a co-maintainer already. Some change in mentorship is already in progress. Mission accomplished. Jia Tan is no part of the project, and he has more right to contribute. All right, so now I want to talk about the technical details and how the backdoor was deploying and how the backdoor works as well. So remember, I mentioned that the user Jia Tan deployed two different test files. The first one was bad3 corrupt underscore LZMA2.exe, and the second one was goodlarge underscore compressed.lzma. And additionally, when he released the latest version 5.6.0 of the exe util package, he shipped the version with an additional file called build2host.m4. If you are not familiar with M4 files, it's a kind of macro file used for configuration during the compilation process. And this file was present in the release, but not in the repository. So let me talk a little bit more about the build2host.m4 file. And I will focus here on the version 5.6.0. So what you see on the screen is just the malicious part of this file, just to focus on what it is exactly doing. But imagine that this file is super big with a lot of different configuration and a lot of legitimate actions. So the ones that you see on the screens are only the malicious part. So first, you can see there is a variable called glam config.make with a grep, which actually look for one of the malicious test files that have been released, and specifically corrupt underscore lzma2.exe. Then we have, in number two additional variables. The first one is here for, which is the tier tool translate, which is basically doing a kind of a substitution algorithm for part of the backdoor itself, the bad3. And the second one is actually showing the file, the test file, and making a sed to retrieve the extension of this file, exe, which will later be used as a command line. And as you can see, the translation of this piece of script is the cat at the end of the presentation. So basically, transforming the itself and decompressing using exe the file which have been deobfuscated kind of using tr. So here you have a look of what was the original bad3 corrupt LZMA2 file before the decryption, the desubstitution, and the decompression using exe, and you have the malicious script on your right. So if you have a look to this malicious script, there is some interesting information here. So first, I highlighted a comment which is actually an hexadecimal string. So today, we still don't know what is exactly these strings, but I believe because in version 5.6.1, this hexadecimal string was not the same. So I believe this string was potentially related to a kind of a versioning number. Then we have a bunch of head commands which are used to manipulate input data stream. And at the end, we have the /3 and backdoor extraction, because in the bad3 corrupt LZMA and the second file, the goodlarge compressed LZMA, there is the next part of the release of the backdoor and also the decompression of an object. I will come to it later. Just let me give you a look a deeper look of what the file,
attack.
what the script
We
is
know
doing
that.
to release
Bots
the next
are
part.
everywhere. They're scanning
So
your
first
servers.
is
They're doing it
decompress the second
fast.
malicious file.
And
Remember
database
the second
servers
test
is
file script is doing to release the next part. So first is decompress the second malicious file. Remember the second test file, good large underscore
At the worst possible moment, like
compressed.lzma
right before a
that
critical
contains
training or
the
something,
stash
it's time to
tree
do the
and the binary backdoor. It removes a bunch of junk data and unused byte because the file is a bit obfuscated. There is again a custom substitution cipher using TR, and then all the deciphered data are decompressed again using XE, which lead to the stash 3, which is another script which is doing a bunch of checking during the compilation process. So let me walk through some of the checking this stash 3 is doing. First, it's check for the iPhone support. Remember previous commit, we discussed about it. Keep that in mind for the next part. Then he verifies CRC source file, CRC64_fastc, and CRC32_fastc for require iPhone code because the backdoor requires this feature. There is a bunch of multiple checks. It verifies the version of the Linux system, validate the GCC compiler, check for the previous two test files, because if the two test files are not present, there is no need to continue to deploy the backdoor. So it's a kind of protection. It ensures position-independent code, and also it extracts the backdoor from the test file good large compressed.lzma.
A heist, right? That's
And this
really
backdoor
exciting stuff that we're here for.
extracted from this file
But before
will
we
be embedded
begin,
into
Aaron, can you tell us a little bit more about like why they should stick around? Like, what does all this actually mean?
Theoretically unclonable, and yet, if you look,
a modification of a function is arch extension supported in CRC x86clml.h, and it replaces get CPU ID with 2 underscore with get CPU ID with 1 underscore. Remember, get CPU ID was where Andres trusts the execution of the backdoor and the amount of CPU usage. So I want to talk a little bit about the backdoor extraction itself because it's quite interesting how the attacker did it as well. So in the code, there is a piece which is using the AWK tools from Linux, and this is actually doing like a kind of a RC4-like algorithm to decrypt the payload itself that will be later stored into the liblzma LS-CRC64. So quite interesting to see that as well. So to recapitulate a little bit the compilation process, because I know it could be quite complex. So first we have the execution of the macro file, the build2host.m4, which is executed and subsequent scripts are also executed. It runs all the checks and it creates the make file if previous conditions are met, because there was a bunch of information. If all the conditions are not met, then the backdoor is not released. Then during the make process, there is a backup of the original file which has been backdoor, liblzma ls-crc64 fast.o. There is a backup because if something goes wrong, the backdoor itself, the code itself can push back the original file, and so there is no track into the final release of the exe util package. There is also some specific compilation flags. iFunc resolvers run at startup. Modification of the file crc64 fast.c and crc32 fast.c. And then finally, compilation, linking stage, manipulation, and cleanup, because the attacker did well. They also have a bunch of cleaning up to avoid any forensic investigation or further investigation. And then at this point, we are here. Malicious liblzma is incorporated into the compiled liblzma. So now I want to talk a little bit more about the backdoor itself and some of the functionalities. So first, it's using the iFunc feature, which allows for dynamic resolution of function implementation during the runtime, meaning it can load some specific features at the runtime. And actually, the backdoor hijacks the ifunc resolver to allow the modification of the global offset table, which is a kind of a table with address to some specific functions. And here on the screen, what you can see is actually the malicious get CPU ID that will trigger the backdoor and continue the execution to the global offset table hijack. Another interesting feature about the backdoor is the usage of dloaded to set up the hook and to bypass railroad and to intercept also redirect function call. If you're not familiar with railroad, it's a kind of a memory protection space to avoid to have some space that could be vulnerable for some vulnerability exploitation. So what it is doing here, so first it's checking that the loaded target process is SSHD, because remember it is our target here, and verify that the shell library, and specifically liblzma, because this is this is where the backdoor is loaded, is already present. Then it set up the DL audit structure to start the audit mechanism. And during the dynamic linking, so think about all these steps are doing during the loading. It resolves and binds symbols. And then the DL audit symbind function is called by the linker whenever a symbol needs binding. And if all the conditions are met, then it sets the backdoor to the install hook function to install the hooking function that the payload will need later. There is also the global offset table redirect, which I mentioned is a kind of a table with a function address. And in that case, at the runtime, the backdoor will manipulate these pointers into the global offset table to redirect calls to the main malware function. And if you have a look to the investigation, if you have a look to the running at this time, everything will look like it's been called through the CPU ID functions. On top of that, there is additional evasion mechanisms and kind of obfuscation. First, there is the strings obfuscation. In that case, what the backdoor is doing is looking for a tree structure. A tree structure is basically a corresponding reference between a strings and a number. And what the backdoor is doing is looking for a specific number to retrieve the strings it needs for the execution of the payload. So if you are familiar, it's kind of API hashing, where you are retrieving the function call based on a specific hash. And in that case, the payload is looking for some specific string, and for example, 0x1d0 is for RSA public decrypt, which is one of the hooked function, or for example, for 0x300 for the ELF header, which is used for the deployment mechanism as well. And you have some of the strings that was extracted by the backdoor and needed for the rest of the execution. So as I said, there is function hook that have been added by the payload itself. So first, what it is doing, it's actually retrieving obfuscated string from the tree structure. And one of the strings which is important here are the RSA public decrypt function, which is a hook, and the RSA get zero key function, which is also a hook. These two functions are used in the latest SSH server version and are called when an RSA certificate is configured, is using for the authentication. Remember that because this is important. And the last function which have been hooked is the EVP PK set1 RSA, which it's a little bit weird because it's not used in the latest SSH version, but probably it has been set up for compatibility or probably for a specific environment. There is a bunch of other checks and evasion used by the sample, by the payload. Here there is an overview. So first, as we saw, it checks that the current process is well SSHD because there is no need to deploy the backdoor if we are not running, if SSHD is not running. It checked for a potential kill switch. So this one is not very clear. This is a string that was present into the malware itself, the payload, but it's not very clear what was the goal of this string. Some researchers are thinking that it could be like a kind of a kill switch. If the backdoor see these strings into the environment, the memory, then it will not run, potentially a kill switch. It also abuses the legit LZMA alloc function for memory allocation, which is required by the payload at some point. And there is also, the backdoor is also hooking the logging function, meaning for every authentication through the backdoor, nothing will be logged into the log of the machine. So that means it's also more difficult for forensic investigation and incident response. And there is a bunch of other advanced functionalities such as encryption, anti-replay. It also embeds its own tiny embedded disassembler, which is required at some point as well. But how does the backdoor works really? So remember, I said there is three main functions that have been hooked, and which is interesting as well is that the backdoor embeds three main functions to be triggered. To trigger this function, there is kind of a magic number, actually three magic numbers, and there is an operation which is used by the backdoor itself, which is magic 1 multiplied by magic 2 plus magic 3, which will give us the command number that will be triggered by the payload itself and the backdoor. So the first one, command 0 and command 1, is actually an SSH authentication bypass using root login. Second one is a remote code execution via systemd, CMD2. And the third one is cleaning close the pre-authentication that have been previously opened. And if you pay attention to the diagram below, to trigger this specific command, the attacker have to embed the payload into an RSA certificate that will be read by the backdoor server during the authentication. And then there is a bunch of decryption. Of course, to exploit this specific backdoor, there is an hard-coded certificate used, so that means only the attacker itself can log in to the compromised server because he already have the private key. So to give you a little more details of how works the certificate payload, so you have here a kind of an overview of what is inside the certificate itself. So first, this certificate is used to the connection to the SSH process to the backdoor server. Then there is an exchange of the public key, and this public key, there is also a SHA-256 which is calculated as well. So let me give you an overview of the certificate itself. First, if you have a look, it's a normal RSA certificate, but there is some interesting information. In the IV, I call that the IV because it's used later, this IV is actually the magic numbers. Remember, the magic numbers are used to calculate the command number that will be interpreted by the server and the backdoor itself. And then, in the modulus N payload, in the modulus N part of the RSA certificate, there is the payload which is encrypted in SHA-20, and this payload is decrypted using the hard-coded ED448 public key that have been exchanged during the initiation of the connection, but only with the first 32 bytes. And it's also using the IV, which are the magic numbers used hard-coded into the malicious RSA key to decrypt the payload. Then, in the decryption of the payload, we have two main parts. The first, which is the signatures, which have been verified by the payload to be sure this is well the attacker that has been trying to connect. And we have the payload itself, which have been executed. And the signature is generated with the CMD value, which have been calculated, a 5-byte flag, which we don't know at this time what is it exactly, the payload itself, and the SHA-256 that have been calculated from the ED448 signature. So a bunch of mechanisms to avoid also the replay of the certificate and to investigate a little bit more. And at this point, Jia Tan is in. So there is a small, let me show you. I did a small demonstration using a payload, using someone reused, recoded actually the backdoor. So I reused this code. So on the right, you have the target, which is the attacker. So what I did here, I recompiled the backdoor itself with my own certificate, so I can reuse the code and authenticate like if I was the attacker. So you have the target on your right. On the bottom, you have the logs, because some researchers found that if you activate the verbose mechanism in the logs and the configuration of SSH, there is a logging feature that appear, and then there is some trace into the logs. So what I'm using here, I'm actually running the backdoor against my server, which have been compromised. And here you can see what I did here is extracting some of the components that have been used to generate the RSA certificate used to authenticate to the compromised server. And as you can see here, you can see the host key, the SHA-256, the different magic number. The magic command, in that case, it's number 2, so I'm using the RCE, remote code execution. And then we have the certificate that have been sent to the compromised server. And if you look to the target here, I've been written a file called it's me, and that have been executed by the certificate itself. And this payload was actually part of the RSA key that are sent to the compromised server. The second one is a remote code execution as well, just to have a reverse shell and to be able to authenticate and to do some action onto the compromised server. Okay, sorry about that. Okay, so you may be wondering who is behind this attack.
The credential itself, or the card itself, controls.
There was multiple personas involved into the deployment of the backdoor for the pressure campaign against Lacey Collin. So remember, I talked about Jigar Kumar, Dennis Hans, and Hans Jensen, and Jia Tan as well. So what I did here, I wanted to know if, because we already had their email address, also their username, and I wanted to understand if there is some connection or if these specific email addresses were known before or not. So what I actually did, I looked for some connection using this email address, especially for the Jia Tan user, and I found out that there was only a few websites that was using this email address. What I found out as well is that for Jigar Kumar, with the Proton mail address, I was able to recover the date of creation of this email address, which was on 2022, April 27, and which is interesting because this email address has been created just a day before Jigar Kumar sent the first email to the XZ utils DL list and project. So Jigar Kumar, Hans Jensen, and Dennis Hans was part of the first pressure campaign. And the second one, Mizo Eter and Grigorin, was part of the second pressure campaign, which occurred between the release of the version 5.6.0 and the release of the version 5.6.1. And which is interesting is that if you have a look to the structure of these email addresses, they all have the same structures. They have a username, they have a number, and they all used a free email service. And also, what I wanted to discover is, does this email address have been for example, known in public data leak database. And I checked for all of them, and all of them were not present in any of the public leaked database. And Brian Krebs, at the time of the investigation, and when everyone was crazy about it, said it's super rare to have one email address which is not present in data leak databases, but it's even more rare to have multiple email addresses which are not present in any of the data leaks, which could give us some information about, you know, a really well-crafted operation. So what can we do about it? Well, it's not an easy question, and I don't think I have the answer today, but here is some elements maybe to, you know, just to think about it. Maybe something that could be done, especially on projects like this one that have been widely used everywhere, will be to have like a strict contributor verification. Also to ensure that the builds are reproducible, meaning to have like the equivalent of the GitHub repository and the release of the tarball. Then audit hooks and railroad protection, but as we saw in that case, the backdoor were actually using bypassing of the railroad. And also improving dependency management could be a good way to improve issues like this one. There is also something which is important to keep in mind, which is what does it mean for the security community and beyond. So first, I think it's important to keep in mind that the entire industry relies on open source tools. And as we saw for the XC util package, some people are relying on hobbyist projects such as the XZ util package. I think also the discovery of the backdoor itself was a mix of luck, coincidence, and expertise, because without the investigation of Andres, then we won't be able to, we probably wouldn't have been able to find the backdoor itself. So I think it's kind of important to think about it. I believe also if you have a look to the sophistication, the mechanism, and the deep understanding of Linux operating systems, I believe it's also redefined what we call sophisticated attacker. And of course, as I said, there is no easy solution. Probably the knowledge of what I'm trying to do today, meaning explaining you how the backdoor is working and what the attacker did, is also maybe part of the solution, because knowledge potentially is the key, so you are well prepared for the next one. Of course, in 45 minutes, it's super difficult to give you the whole details. There is a bunch of technical details into the backdoor itself. There is a lot of information to cover. So I want to acknowledge all the researchers that have been working on it, because they did a fantastic job, and I really recommend you to have a look to the different blogs at the end if you want to learn more about it. And because of, thanks to all their write-up, we know a little bit more today how the backdoor works, but there is potentially more to discover and potentially stuff that we will never discover. And before to conclude on the presentation, I just want you to ask you a question to think about for potentially the rest of the day, the rest of the week, or potentially the rest of your career. How many other Jia Tan do you think are paid to insert backdoors in open source projects? And thank you very much for listening to me today.
order to clone it because there was no validation.